Okay, for people joining this live stream, I am continuing, at least for another few days, my crazy pursuit of combinators. And topic of the day has to do with compiling Lambda expressions to combinators and how one does that. So the question that I'm asking is, what is the optimal compilation of a Lambda expression to combinators? And the thing I'm trying to figure out, first thing I want to know, let's see, I had already computed a bunch of these, and Max has some faster code for computing this. So what this is doing is it's finding, let's say, find lambdas of 4, 2. That will find all combinator expressions which can be represented as pure lambda terms, right? And so in this case, then the thing that we might do here, so there's a standard algorithm for turning, which I think I have a version of. Let me just look at that. I wonder whether it will work with numbers in place of symbols there. Let's take a look here.
Yes, it does work.
No, yours does, but I'm wondering whether my standard, here, let me look at this. Combinator construction.
So you might need to explain what you're actually doing here, because it's not that obvious.
Okay, fair enough. All right, so let's take this expression, S of S of S of K, here like this. So this will be combinator fixed point list of this. That's a combinator expression applied to 1, 2, should generate a sequence of combinator forms that eventually turns into 1 of 2, where 1 and 2 could be variables. So let me just see. If I say SK combinator compile, 1 of 2, and vars is 1, 2 here. Okay, so that gives a simpler version there of the compilation of that. So let's try 1 of 2 of 2. Okay, whereas here, 1 of 2 of 2 is this thing here. So in other words, we found, so this is like the ultimate optimizing compiler question of, can we optimize our, what is the absolutely optimal expression? What is the shortest program that computes this thing, where this thing can be thought of as a lambda expression, lambda x, y, etc. Okay, so what I had previously been doing is I want to know of all expressions, so I can count. Okay, so let me just summarize here. So this is now, okay, so how many of the lambdas can we get with how large a combinator expression? Okay, so that's, so now the question is, how many lambdas are there? Let's see. Oh, and by the way, Max, you are using certain limits, which presumably are going to be pretty safe, where we're, in terms of how large the intermediate expressions can be.
Yeah, I added the limit on the leaf count, which is now it's computing it in real time.
Okay.
So it's not really necessary for evolution performance, because I mean, so it's always linear pretty much, but it makes this code faster because it was doing it before, and it saves some computations if you do that.
Okay. Okay, so this is enumerate lambdas. So this is, so if I say enumerate lambdas, enumerate lambdas of 4, 2, that will give us all of the expressions of leaf count 4 that are lambda terms of that size, and there are 80 of those. Do we know how many of these there are? Do we have an expression for how many of these there are? Should be pretty straightforward. If necessary, I wonder if we could see if Ed Peg happens to be around. Could somebody see?
Yep.
Okay, thanks. He would know this immediately. I don't know whether this is Catalan numbers or something different.
Well, for each range, it's Catalan of 3, but how many ranges are there? How many tuples are there? The number of tuples times Catalan of 4 minus 1, I would guess.
Okay. Okay. But then here, okay, so those are the lambdas. Now, the question is, of those, how many are we getting? So I had started computing this, and maybe your code is so much faster that we should just use it, Max. Let's see, what I had done was I was computing let's see here. What is this? This is, oh, I see. This is now computing for each, for this particular lambda term here. Okay, so are you caching your find lambdas, Max?
Oh.
Okay. So let's go ahead and make a lambdas table. I mean, the problem is that we've got a lot of copies of one particular thing. Like we compute the same lambda term in a zillion different ways. See what I'm saying?
Yeah. Well, I'm sure there are also a lot of repeats in the evaluation of the combinators itself.
What do you mean by that? I mean,
well, if you have different combinators, probably they have common sub-expressions which evaluate in the same way.
I see. But
you have to move all of it to C++ to make that happen.
Well, we're not going to do that. I mean, you know, your caching thing, which I'm sure we could implement perfectly well at top level, but we haven't, but that's okay. Okay. So that's not the relevant point here. The relevant point is, okay, so I have some pictures. There's a picture. I don't know why these dots suddenly become so hard to see here. It's really weird. Okay, so this is the running time of computing one of two of one with combinators, okay, with different combinator expressions. Okay, so I think the first thing we need to do is take, okay, so let's enumerate lambdas 2, 2, okay? And then the question is, let's find, in terms of combinators, what the optimal combinators for computing all of those are, and how far we have to go before we get all of those things, right?
I mean, you have a natural upper bound, right? I mean, you can do combinator compiled, and you know one way of doing it.
Indeed. Right. How big is combinator compile? How big does it generate?
Well, that recurses all the way down, and each time it generates an S term. And at the end, the k term, so probably exponential.
Okay, so let's just do this. 1, 2, I think there.
Stephen, Ed is here.
Okay, thanks. So Ed, we would like to know some little bit of combinatorial stuff. Okay, so that's a good thing. So the original compiler, Ed, how many distinct things are there of this form that have n, leaf count n, and k symbols? Ed?
I'll think of it. So all possible S and K possibilities?
You can think of it that way, but I want k symbols altogether. So I'm just asking, and maybe we already have that we want it for the case of k objects, right? Or possible, I mean, it'd be Catalan numbers if it was just
if it was just S, yes. And if it was just 1K and the rest S, then it would be basically.
I don't want 1K. I want all possible positions I want k symbols in all possible positions. Okay.
If you look at the definition where we had the groupings and the tuples, then I think you should be able to figure it out, because how many tuples are there, and for each choice of tuples you have Catalan of that many groupings, right?
Okay, so the tuples is just k to the n, right?
It would be Catalan number times the length, 2 to the power of the length.
So, okay, just a minute. Okay, so you're saying count lambdas of n blank, k blank is what?
Catalan number of which one is the length? K?
K is the number of symbols.
Yes. K.
Oh, K is the number of symbols. So it's 2 to the n times Catalan.
2 to the n, where n is the leaf count.
Yes.
Okay, times Catalan of what?
N.
And what about k?
Instead of k, it's instead of 2, it's k.
K to the n times Catalan of n.
Right.
All right, so let's try that for count lambdas of 4, 2. Nope, you're wrong.
No. Catalan number of n minus 1.
Well, it's data point. One data point is correct. Okay, well, let's assume that's right for now. Let's get our upper bound straightened out for the standard compiler here. Okay, and maybe it's obvious. Maybe it's obvious to Ed. I'll put this compiler up on the screen there. Maybe it's obvious how long that can end up being, but let's try. Okay. So let's go ahead and say leaf count of this. Okay, so now let's go ahead and do this. Hard to tell what this is. Maybe this is obvious. Let's try 4. Now let's do accounts of that. Okay, Ed, this is your number recognition moment. Oh gosh. You know, none of these things are ever simple. Wow. Even from the most basic compilation. So how are we thinking about this compilation? This compilation is basically just taking, I see, it's unraveling f of g into an s, right?
Yes, and then it depends on whether the innermost one is the variable you're looking for, because then it turns into an identity, and if you don't use the I symbol, then each identity gives you 3 gives you skk, right? So it really depends on what the innermost leaf, whether the leaves are 1 or 2, and that's why it's probably so irregular.
Okay, but so if I were to do this, well, then it's just trivial, right? If I do this, right? If I just have a single thing inside it.
You don't need a second variable in the compilation here, I think.
Okay.
Well, that's the skk that we got rid of.
Okay, all right, fine. So this particular thing, if we just do, and just because I like to be careful, let's just do this. That's just, what is that? Oh, that's just quadratic, yes? Is that right? With a single term, it's quadratic. Am I correct? Hello?
Looks like it.
Okay. All right, so then in the case of, okay, so single variable, it seems to be that with respect to size n, oh, it's not even quadratic, it's linear. I'm being stupid. Single variable, it's just 4n minus 1 is the combinator size. And by the way, the combinator,
let's see some of them, I mean, just to make sure that that it's all correct.
looks okay to me. All right, let's try doing our own find lambdas with one variable here and see what the corresponding thing is for that.
Yeah, I think you have here, you have 3 symbols for the skk for each variable, and then 1 s for each of them. So that gives you 4n.
Okay. Okay, so let's go down here and okay. So then what we want is we're going enumerate lambda. So we're doing compilation, which means find lambdas of n, let's say 4, 1. That's uninspiring. So all of those are just the one, just one. So let's try this. Okay, what happened here? Why are the only lambda terms that we can get? Maybe we just don't have enough yet. Maybe we don't have enough. Maybe we need 7 because that thing said we needed 7. Okay, so let's go ahead and okay, let me just see, how do I do this? I just want to pick this up. Okay, so let's go ahead and gather by. I just don't want to generate just well, okay, let's just do the 7 case we can print it out, but then we should do something more systematic. Why is this taking any significant time?
Well, there is, well, first of all, there is an overhead with study and parallel map. I don't know what to do with, but I don't know why it's actually running a long time.
So what
the end of the second row there seems weird.
Okay.
So you have just 3 different ones, yes.
Okay, so let's go ahead and count percent 215. So let's say what I was originally going to do was I was going to say, okay, so basically up to 6. Okay, so up to leaf count up to size 6 only get 1.
I thought I saw a 1 of 1 in there as well.
Okay, well, let's check it. Let's check it. Let's check it. Let's check it. Let's be more careful. Okay, let's be more careful. So let's do this. Let's say gather by.
Before that, could you do a tally and double percentage?
It's not going to be a tally. It's going to be hold on. We'll get it. Just do not panic here.
I want to panic.
Okay, let's do a gather by here on the 5s, for example, and then let's say gather by last, and then let's say for each of those, let's map onto that. Let's say hash sub 1 minus 1. That will give us the thing, length of hash. And let's just for good measure say the first, just so we see what an example term is. Okay. Okay, so there are 38 things that all generate just a single 1 in the case of the 5s. So let's check that. Let's go up all the way from let's say from n is 1 to, let's say, let's just do up to 7. Okay, make sense? Okay, so here, okay, the first time there's a 1 of 1, and there's a single 1 that does that at length, whatever this is, 1, 2, 3, 4, 5, 6. At length 6, there's a single 1 of 1 that's there, right? At length 7, there's 11 1 of 1s. Okay. At length 7, there's a 1 of 1 of 1 as well, right?
Have we looked at that 6 case in any other?
Which 6 case?
The unique 6 case there.
No, but let's look at it. Okay, so let's look at that. Combinator fixed point list of that. So what should happen is that of 1, boy, it's doing a lot of messing around to get to that. So eventually it gets to 1 of 1 with a fairly slow, the length of that is 9. Okay, now if we were to look at this one here, we've got 11 of these guys. So actually, let's use that as our first example of sort of computational complexity theory in action. Okay, so in the 7s, we want cases of %215 that have the right-hand side of the form blank. Oh gosh, this is a crazy thing, right? How do anybody know how I verbatimify the cases?
You could just pick the ones that are not 1 at the end. And you'll get 15 cases.
Do I do this? No, that doesn't work, Ed. The issue is this. It's X blank arrow 1 of 1. Wait a minute, the 7s case. Oh, I should have done lambdas of 6, right? No, I'm sorry, I'm doing the 7s case. I'm doing the 7s case. I'm doing this case here. And then I want to say that whole thing, arrow X. Okay, there we go. Oh, I see. Those are all the combinator expressions that generate. Okay, so these now if I say hash sub 1 and I say combinator fixed point list, okay, length slash at that. Okay, so that's kind of cool. So that's our sort of simplest version of computational complexity theory.
Let's do a repeat on that on the 4 cases.
On the which cases?
The 4 1 1 1 cases.
We will, but hold on a second. Before we do that, I want to try something else. I want to say max of leaf count. Max of leaf count slash at sign the blah 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 whatever that thing slash at %223. So that is essentially giving us the memory complexity. So that says that there's something there which is faster but has higher memory complexity. Makes sense? It's kind of a minimal version of computational complexity theory. So
what ordering or strategy do you use here? Just
leftmost, innermost.
Okay.
So one thing that might be interesting to plot is, so let's try and make sort of our time memory trade-off, right? So for a given thing, 1 of 1, what we're seeing here is list plot of, and in general, we want to make a bubble chart of how many things there are. Okay, so let's go ahead and do that. Okay, so then let's say, we got a list. So, okay, so let's make a time mem plot of a list, and that's going to be bubble chart. Okay, so essentially what we're doing is, for each of those things in that list, we're going to say combinator. Oh, actually, what we want to do is args here. Combinator fixed point list of hash of, oh gosh. Now, you know what? I'll just do the list here. I'll insert the okay, combinator fixed point list of that hash, and then what I want to do there, slash at combinator fixed point list of, it's going to be, right, so for each of these, what I want to do is I want to look at the length, which is the time complexity. And I want to look at the max of leaf count, which is the memory complexity. Not the average memory use, but it's the total memory use, right? Make sense? So that of combinator fixed point list of, and am I getting my braces correct here? My bracketing correct? Yes, I think so. That slash list, and then what I want to do is I want to make counts of that, and then I want to say key value map of append #1, #2. I don't even probably need the #1, #2 there of that, and then I'm going to make a bubble chart of that thing. Okay, so this time mem plot, I want to take %223. No, where is it? It's the cases, these cases here, %222 of 1. No, shoot. I want to say hash of 1 slash at that. And that should give me, okay, there we go. So that's the number of things that are of each time complexity and so on, right? So now I should be able to just say bubble chart of that. Okay, so that is giving us the time memory trade-off and the number of different programs that are that size. Oh, Oh, I see. Oh, the problem here is that this is really, it's a three-dimensional thing because we need to also know the program size, right?
Why do you say leaf count is a memory use?
It's the max leaf count. It's the largest intermediate expression size.
Yeah, but you don't need to keep all of the leaves in memory separately.
I don't care. I don't care. It's a proxy for that. I mean, I understand
Well,
the
not
implementation.
really.
The implementation is different.
Exponential algebra.
Okay, fine. Okay, but this is the trade-off between time. Okay, so let's look at the analogous thing for the next one up, right? Find lambdas of 8, 1. Which I think I have independently computed. So let's see if this can be computed reasonably fast. If not, I'll use my version of it. What's it doing right now?
As far as I understand, it's copying the inputs to other kernels. I have no idea why it takes so long.
Roman, you're the world expert.
Well, not on parallel map, on that version of parallel map, but.
Well, okay, so the question of what granularity parallel map monitored is using and whether it takes.
It's not granularity. I tried different ones. It's always the same. I mean, why does copying takes any large time at all? Because, I mean.
Okay, let's now find out. Okay, first question is, let's do this. FL81. Okay, so those are the things you can compute, right? So notice that even among the 3-leaf cases, I don't think we have all of them yet. Right? If I say enumerate lambdas, oh, we do have all of them. Okay. But we certainly don't have all of them for the 4 case yet. Okay. So let's see here. So we want to do the same thing. What was I computing here? Were these the 1 of 1s? Yes. So I want to do this. FL81. Then I want to say hash of 1 / at that. And then I want to say time memplot. And then I want to say bubble chart. That's kind of cool, I think. So that's showing.
No,
What's that?
In 230, there's one rather strange output there. The beginning of the second line.
This puppy.
Yes, I mean, this shouldn't be here, right?
Why not?
That's way too big. I mean, you went up to how many?
No. No, this is, remember, what find lambdas is doing is it's trying combinator expressions up to size 8. And so that creature is like a busy beaver.
Okay, so it's the other way around. Yes, you limit the combinator size and you see what it can generate. Okay.
Right. So that one there, I mean, just to show that.
Remarkable, right?
Oh, it's I don't know. I'm a seasoned traveler in the computational universe. I don't find it that remarkable. It's only remarkable if you're not used to seeing all this weird stuff happen. Yes, I agree. It's remarkable. I don't think it's a as remarkable as other people might think it was, but yes. Okay, so this is a beaver. It's not even a very big beaver. It doesn't even take it very long. It just goes and it's, you know, it's building its dam very quickly. Okay. So, okay, let me just check one thing here. Yep, okay. So this is basically showing as the program size increases, I mean, it'd be nice to have a plot that shows all three of program size, memory size, and time complexity. So I think that can be done with essentially bubble chart 3D, if I'm not mistaken, which would then just prepend the memory size, I mean, the program size to the thing. So let's try that. So what we have here is the corresponding thing. Let's do this case. So now what we do is we do the case of 6, right? Which I hope was really fast. Oh, don't tell me we have. Okay, there we go. Okay, so what we're doing here is in the bubble chart 3D, what we want to do is we want to have this one. So we're going to make the complete list is this one, then this one here, then this one here. And now what we then want to say is we want to say map indexed Richard on our live stream is pointing us to a page which we can look at, but map indexed of a prepend. I think we want a prepend here. Prepend first of hash 2. No, prepend hash comma first of hash 2 to that, and we want a map at level 2. And then we want to say bubble chart 3D. There is a bubble chart 3D, isn't there? Yes, there is. Well, there we have it. Okay, so that's showing us. That's an amusing picture, I think. Do you understand what this is showing, right? So this is showing the different colors here, unless I'm very confused, show us the different you know, program sizes. And now then this is showing us the time memory trade-off for those things. Makes sense? I think the vertical height is time. I think so. Okay. So the first question is kind of the what's the most efficient? So of these, the first number is the time, right? So the most efficient are these one. This guy here. These ones here are the most efficient. So in this parallel outermost kind of way of doing it. So that's saying that in here, %223, so fastest are select in %223 length of combinator fixed point list equals 6. Oh, come on. Wait a minute. I didn't mean that. I meant %222. and then I wanted to do of this, of 1.
Yes.
Okay, so those are the winners. Those are our winning, those are the fastest versions. So notice that those ones are, now how do they compare to the what we've got for just 1 of 1? The smallest we have here is a size 6 one, whereas the smallest we have from ordinary compilation here let's see. Okay, so we just want to say SK Combinator compile. Okay, so this is really the case of 1 of 1. And that one is, if we say SK Combinator compile 1 of 1, okay, so our optimizer in this case manages to do 1 better than the generic compiler.
Now, speaking of optimization, please go down to the beaver where you, what I find strange here, that this input term is not in normal form.
Oh, you know what?
No, in fact, yes, but
I forgot. I forgot. This is the beaver here. So this is.
Yes, but what I meant is if you try the old.
Oh, I see. I see what you're saying. Yes, it wasn't.
Why
a normal
isn't that reduced? Why isn't that?
Well, why should it be? Just enumerating combinators. It doesn't have that. It doesn't.
Yeah, would you ever return like a half compiled program?
Well, you mean a program that that
has redexes in it. I mean,
programs that runs on import, which we do pretty often.
You mean programs that run without their input?
Yes.
Well, so you're saying
they run when you import them.
Yes, they do. Right.
Set replace actually, so it's not that unusual.
Okay, so in that case, what that's doing is that thing is pre-computing. You can pre-compute this.
Mm-hmm.
And then given that, you have fewer steps. So now if I say list step plot of leaf count that of 1.
Mm-hmm.
It didn't save it very much.
I'm trying to understand what, I mean, there is of course a notion of a program that first writes something and then interprets some other program on the Turing tape, which is quite a powerful notion for complexity, for doing complexity, thinking about complexity. But whether this could be considered something like that.
Well, I think this is, okay, so the notable thing is it evaluates the pure program. The pure program evaluates before it applied to it. By the way, and if you're curious about some historical stuff for my history adventure here, I was just looking at that thing. That's John McCarthy's original paper about Lisp, trying to understand how much he actually thinks he understood about lambda expressions here. Later on, he talks something about combinators later on, but I don't think this is. Dana has always claimed that John McCarthy didn't really understand lambdas. And previously, John McCarthy had worked on Turing machines. As a paper about Anyway, I do find it amusing that the M expression form of Lisp that was never used in the end looks very much like Wolfram language. It even has square brackets. Did you know that? I didn't know that.
No.
The original car open bracket with the square brackets. Look, right there. If you go in, see that? Doesn't that look just like modern times? Except they have semicolons for function arguments. It's a pity John McCarthy was always so upset about the stuff we did. Oh well, so it goes. Anyway. Somebody's asking the name of the paper. It is called Recursive Functions of Symbolic Expressions and Their Computation by Machine, Part 1. Part 2 was never produced. Okay. So I want to go back here. So what we've got here, we've got a sort of minimal example is even with one of one, it's already interesting to look at this sort of computational complexity thing. So let's try and get FL91, okay? Let's just see what that looks like, just to see how that sort of stacks up. If we can just compute this thing. While we're talking, we can compute it. Okay, let's see. John Trump has a lot of examples of this on his page. Okay, so let's take a look at this. You can certainly look at that. There's so much to wow, okay, recent paper about this stuff. Oh boy, I cannot be expected to read the whole literature as I try and summarize this stuff. By the way, for anybody on the live stream who's interested, Monday, don't miss it. I'll bring it up on the screen, our promo for it. Hold on one second. Oh, where is it? Where is it? Where is it? Here we go. Not to be missed. At a strange time. It's a pity. It's very early in the day for me. Noon Eastern time. It's good for Romanies in Europe. Did you see this invite yet, Roman?
Not this form. I saw an early draft.
Needless to say, that does evaluate to this. I wonder how many people have got this invite, which includes many of the, well, I hope most of the people who've really worked hard on combinators, although it looks like we should be inviting another person here, this John Trump person. This should be, okay. Anyway, binary representations, both lambda calculus and combinatory logic, okay. Oh boy, the De Broglie notation. Did you ever meet De Broglie, Roman?
No, I didn't.
Nor did I, unfortunately. Oh, this isn't, well, let's see. Okay, it's interesting. Well, great. Okay, I don't think it's somewhat relevant, but not You know, the number of people who've been involved with combinators at some point is just crazy large. I just had mail from Simon Peyton Jones, who comments that his very first published paper was about combinators. Okay, implemented a lambda calculus reducer in binary lambda calculus itself. That's cool, actually. That is cool. Yeah, this binary lambda calculus does look somewhat interesting. Oh, I see. This is part of the algorithmic complexity crowd. Yeah, Parmenides on a live stream observes that the originator of Haskell, the fact that the originator of Haskell was doing combinators first is fitting. Okay, let's go check our version of this here. Let's go get this thing, pick this thing up. FL91. Okay, and let's do our bubble chart of this. Take a look at our time memory complexity for this thing. Okay, there's some very, very, very dumb combinators there. That is a very busy beavery dumb combinator right there. So unfortunately, I didn't bother to record which one oh, I see. This time memplot, what I have to do here is I have to know, I should find what that busy beaver, you know, combinator is. But that's so one question here is what the min, let's see, the first slash at, I can't imagine that these are getting any more efficient. I think they're getting very inefficient because they probably have to read their, they have to read the program first. Oh, 6. There's still a 6. That was the same efficiency we had before, right?
No, I don't think it will get any better, right? I mean,
no, it can't get better.
No.
It can only get worse. It can only get worse as it tries to consume the program.
Yeah, if you just decorate the program with useless side computations, then it, I mean, there's no.
Right, I'm sure that from here on out it just gets worse. But let's try just 247 there. Very inefficient way of doing this, but let's go ahead and do it that way anyway, just to see what it looks like. Okay, so it's basically getting, I mean, we probably should normalize them differently, but that's basically okay, Richard is commenting, we're wondering whether the lambda to SK compilation process could be implemented using non-deterministic rewrite rules. I bet it can. I bet it can. But that's probably not, I mean, one of my main objectives here is not to get into too many rat holes because I'm desperately trying to finish whatever I'm writing right now. Okay, so we're looking, let's just look at the single variable case, just a few more iterations on single variable, and then let's look at larger variables. So the next question is, of the various things that we see here in this, okay, so the next question is, what can one compute? AKA algorithmic complexity of various. So the thing we were doing previously was basically asking, it's empirical computational complexity theory, basically. What is the time and memory? You know, in other words, given a particular program, okay, various computations here. So that's a different thing. So the first step is kind of traditional computational complexity theory applied to these systems, given that you scan over all possible programs. So you're looking at all possible programs. What what's the most efficient way to compute this? Okay, so that's sort of step one, and I'm going to take some other notes here because I want to organize myself here. So sort of step one is time plus memory complexity, scanning over all possible programs. Well, time plus memory plus, yeah, I guess for a particular simple case. Okay, so now the question is, what can one compute? In other words, another version of this is, what are the, quotes, most natural things to compute with combinators? And that's sort of interesting because if you think about using, I mean, one of my crazy ideas of recent times is to use combinators for chemical computation, to think about combinators as actual, what happens if you actually try and implement a combinator with molecules, or something like a combinator with molecules. And then the question is, what are the most natural things to build if you're doing that? Which is analogous to, what chemicals can you, compare, what chemicals are most commonly synthesized.
Now, how do you deal with argument duplication when you have actual substances there, rather than symbols?
Well, good question. I mean, it may be that a better model for chemicals. I mean, maybe combinators as such aren't the best model for the chemical case.
I mean, there's a notion of linear lambda calculus, which never, where a variable never occurs twice. So you can never create something out of nothing.
Look, it's not obvious to me. I mean, I'm saying this too glibly with combinators because I agree that the copying, which is the way that combinators differ from our hypergraph models, is the fact that they have all this giant subtree copying, which is, I agree, maybe not a chemically sensible thing. Maybe there's a different minimal model that one should pick for the chemical case. I really wanted to do this project for like 40 years or something of making an actual, universal computer at the chemical level, which is kind of what we humans, biological systems are, but we are surely not the optimal molecular scale universal computation system. Wouldn't it be fun to have the optimal one, or at least a closer to optimal one? And then it's kind of like generalized chemistry, so to speak. Okay, but now we're on to what can we compute. So let's say, oh boy, we got found the primitive recursive functions are recursively enumerable. Chem lambda, okay. Somebody's. What is this? Graph rewriting system derived from graphic lambda calculus. Okay, that's cool. Oh wow. Even, this is where I get so embarrassed. It was even published in our complex systems journal. Oh, and this is the person I know. Okay, small world. Let's look at this. Shall I click the journal link and embarrass myself that we've done the wrong thing with yeah, I can do that. Okay. Wow. Cool. Well, I'm glad that we're publishing good papers.
Looks like physics. Yeah.
Well, it looks a little bit like, yeah, this is interesting. This is a good paper. It looks like a good thing. Maybe we should add it to our list of ones relevant to the physics project. Wow, what the heck is this?
I'll pass that along to be added.
Well, I'm not certain. Somebody should look at it. I'm not sure it's totally relevant.
Yeah.
But
Okay.
oh my gosh, the combinators here. I'm telling you, combinators just seep into all kinds of different places. Cool. What is this? A left to the interested reader. That's always the
You need to say that somewhere in your blog.
what? A left to the interested reader? Yeah, the left to the interested reader, human or AI. What is all this stuff? Oh boy. Well, looks interesting. Don't quite understand all of this. Okay. Well, that's interesting.
Another thing that
For
would
that pointer.
be fun to identify in these compiled combinators. I mean, we have all these cases of 1 of 1 of 1 of 1. These are, of course, just the church numerals, right? Church numeral for k applied to 1 of 1 gives 1 of 1 of 1 of 1 of 1 k times.
Wow. That's a well, gosh, somebody should invite this chap to our combinator party.
I will add it to the list.
Huh. Well, okay, this says that there's a way to this thing makes empty eggs. Cool. Well, okay. Thanks. Well, this is the good thing about doing these live streams is people point out all kinds of interesting things that exist that I did not know about. Well, thanks for this one. Okay. This is a very recent. Well, interesting. Okay. All right. Okay. All right. So let's go back to. Boy, I have to not get distracted here. I'm trying to finish a bunch of things before the I'm now see this is called shiny intellectual objects, and the question is what does one chase in Right. Definitely something to, yeah. I mean, this question about whether one can really make realistic chemical processes that, you know, in other words, make a sort of a, I mean, it's not an artificial chemistry, a real chemistry, where you pick some actual type of molecule that isn't DNA and the whole crazy apparatus that us biological organisms use. And nevertheless, you know, in other words, you're starting from some sort of a, you know, the trick is function application then becomes, you've got one, you know, you're mixing together bottles of chemicals, basically, is function application. And what can you make that way? And can you, for example, have things where, yes. Fascinating. Okay. Okay, sorry, I shouldn't get too distracted with this. All right, let's go back to the and I'm also you know, I was also getting distracted earlier today thinking about this vision of a world without nouns. If you believe in combinators, you don't believe in variable names, and that the sort of the natural kind of the natural thing to ask is, what does everything look like if there just aren't any nouns or pronouns? And is that, you know, if you were an AI as opposed to one of us humans built with the brains and structure and language and so on that we have, could you think without nouns, so to speak? And that's anyway, that's a I never really thought about that before. Okay, we got the wrong group of people to discuss thinking without nouns here. All right, let's get back to actual combinators, and then I want to. Okay, so the thing I was going to do next was to ask the question of these things: what actual let's say we go last FL81 here, and now we want to say counts of that. Oops. And then let's do a key sort on that. Okay, so this is showing the number of different, there's a very limited number of things that we're getting here. So we're getting all the 3s, but we're not getting even all the 4s yet, right? Did we do in the 9 case? Was that what we just did? Yes, it was. Okay, so in the 9's case, okay, the 9's case we've got, so if we look at the distribution of leaf counts over the keys there, that's kind of silly and annoying that it doesn't sort by leaf count, but that's okay. So let's say counts of this key sort. So that's saying, okay, we've got 4, 4 here, and 4, 4 should have been, if we do enumerate lambdas, that would be, so 3, 1 is length 2, and we have both of those there. 4, 1 is puffle. Okay, so there's one that doesn't get computed yet. So there's the hardest to compute function, right? Or at least the least, you know what I'm saying? The least, so what we want to know here is complement of enumerate lambdas in last slash at FL91. Okay, so that object is not computable by any combinator expression up to size 9.
That's an interesting one. That's just the nesting function.
Yes. Yes.
Will it be 10? It seems that it goes 1, 3, 6, and we know that 9 doesn't work, so it seems...
What goes 1 through 6?
It seems like it might be triangular numbers.
You mean to compute this object?
Right.
Well, an interesting question is what actually computes the in the other one. So if I say cases of FL, let's say 6.1, I don't have that. Oh, blah. Let me just compute that just for the sake of having it. FL 6.1 is find lambdas 6,1. Okay, great. Cases of FL 6.1, comma, and then I got to do this crazy thing. Let's see. What do I want to say? 1 of 1 of 1, if I'm not mistaken. Arrow X. Oops, isn't there? Okay, so it's in 7s, presumably. Did I get this wrong? Did I not have a 7? I thought I did the 7s. FL8. Oh, 7's a percent. Okay, well, let me just do it here. FL7.1 equals %215. Okay, so now down here, really? Okay. So the first case where this shows up is at the 8s, where we get 1 of 1 of 1. So
It's the special one you got at 6.
which one I got at 6?
There's a unique case, I think, with the 6s.
No, that was for 1 of 1.
Okay.
I think, if I'm not mistaken. Yeah, that was for 1 of 1. I had it at 6s. Okay, so 1 of 1 was at 6s. 1 of 1 of 1. Okay, so summary. 1 of 1 occurs for size 6. 1 of 1 of 1. Oops, no, that's not that one. 1 of 1 of 1 needs size 8. And of those size 8 things, we're going to say length. Well, we can do time memplot of %264. Oops. Hash of 1 %264. Wow, that's quite diverse. I mean, so that one there is definitely that one there is the most efficient. So if I do leaf count /@ Combinator fixed point list of hash, %264, oops, that thing of 1. And then I want to say list step plot. Okay, that's all the computations. So that's all the different ways to compute 1 of 1 of 1 with and so that that is the most efficient one there. 9, 15. Oh, there are 4 copies of the 915 case. So these are the cases here where, right, so there are a bunch of different ones of these that all compute that efficiently, so to speak.
They look identical. I mean,
yeah, but they probably.
Well, probably just the order of evaluations, right? I mean, if you have 2 identical sub-expressions that reduce, then it doesn't work.
May as well do 10.
10 watts. The size 10, you mean? Did I already compute?
Right.
Well, I don't think. I mean, it's interesting that we already can see non-trivial stuff going on just with one argument. We don't even need to go to the 2-argument case. I don't know whether we're going to see different stuff for 2-argument. Let's see. Okay, again, what happened with the, okay, so for the regular compiler, we just got linear increase in the sizes. So, and what we're seeing here, linear increase in the maximum size, right? No, the regular compiler, every lambda, right, the regular compiler, 4n minus 1 is the combinator size for all 1-argument functions. One argument functions, basically, 1-argument lambdas. Whereas in the case where we're just looking at lambda, combinators, we get different sizes for different, for different cases. Okay. Well, what else can we figure out here quickly? So what we're seeing is, in this case, the 1 of 1 of 1 case, let's see, we had failed to find, this one here, we haven't yet computed even at 9. But that is a case of 4, and 4n minus 1, in that case, for the ordinary compiler, 4n minus 1 is otherwise known as 15. So we're way ahead of the game here. What we're doing here is generating vastly more efficient things than we would be doing there. Okay, so let's look. I guess we can try doing the, all right, let's just do it. FL10.1. Let's find lambdas 10, 1. Now this might, it might just take too long. And we probably should be storing these things here. But let's just think if there's anything else we can quickly do. So what we're looking at here, for a given function, we're asking the question, what is the highest algorithmic complexity function for, and what we're saying is that at least in this case here, it's this 1 of 1 of 1, this rather boring function here, is sort of the highest algorithmic complexity with respect to with respect to combinators, right? Yeah. So what else can we figure out here? So we could also ask the same question for, for more complicated functions, but I think it's going to be sort of the same story again. And this is, these are essentially the memory size traces with our other stupid way of doing the evaluation. Now, obviously, you'd get different results if you chose a different evaluation order. Okay, well, anyway, I mean, we can see whether this runs here. Any other thoughts that people have on I think this is in my attempt to give sort of the centennial summary of what's happening with combinators. I think there's interesting things here. Anything else that we should consider right now? I mean, in other words, is there any other obvious thing to do? I mean, so we were looking here, is there a better way to display what we're seeing here, which is there's several things. How many different programs are there of a particular type? I don't know that's not really a thing that one thinks about in algorithmic complexity theory, is sort of how many programs are there of a given type. It's kind of the program entropy, given, that's actually an interesting concept. Program entropy for computing a given function, how many distinct programs do it? That's a different thing from, and obviously those different programs can do it at different speeds and all that kind of thing. I had computed this stuff for cellular automata at one point for computing. Yeah. All right. Well, okay. We've got a parallel map starting up here. Let's just see whether we actually can really. Okay. Anybody got a better idea for how we plot these? And also we have this ridiculous beaver here that's just like spending an awful. Did we plot what that one actually does? No, I don't think we did. The thing that really takes an absurd amount of time to compute that function. And maybe we should do that, but okay, let's just see this run. Meanwhile, I'm sorry that Chem Lambda guy didn't look at a bunch of stuff in NKS about things related to this. Oh well. It's too high an information density, I suppose.
I think this has as many cases as 1010 case, which I tried to run, and it at least takes a few minutes for it to start.
Are we actually saving something by running this with a 1 in the second argument, or are we, in other words, could we run all of them in parallel? Would that make sense? No, it doesn't. You can't do that, because that's the difference in this intensive and extensive combinator stuff and so on. In other words, it's whether you apply it to arguments or not matters.
Right.
Well, I was trying to untangle. Okay, here's a question for Roman. He might know the answer.
You could pre-compute all the normal terms, right, by reducing them without arguments first, because that's the.
It doesn't help you very much. It doesn't help you much. No? It's not that contractive a system. Mm-hmm. I mean, I've tried that. The fraction of things that are not, there are plenty that aren't in normal form, but the number of distinct normal forms is large compared to the number of initial forms. That is, it's not the case that many initial cases evolve to the same normal forms. Hey, I've got
the optimal thing probably would be to run them all at once. Basically, we create one giant DAG which can install, I mean, assuming it fits in memory, and then we can just run them all without ever evaluating the same expression twice.
If you can do that, that would be wonderful.
Yeah, I mean, I certainly can do that, but probably not by tomorrow.
Well, okay, so I have a history question. Roman, you might know the answer to this. I don't know. So I'm trying to track down the history, to what extent combinator ideas affected early programming languages. And particularly, I'm curious about Algol 60, which I don't know very much about. And most of what was in there, I mean, the idea that a function could return a function and things, I think was sort of in there by then. Do you know anything about this?
Well, I think that was one of the distinctive features of Algol 60, that it could actually return functions.
But how did it do that? I mean, it returned the analog of function pointers?
I don't know. I mean, I've never worked with it. So.
No, I don't think it was ever implemented properly. And I think it's one of these things that was a theoretical, I think it's the best known unimplemented programming language in some sense. Yeah, and I mean, I don't quite understand. Yeah, okay.
I mean, actually, I think that would be Mix from Donald Knuth.
There's got to be an implementation of Mix by now. Okay, well. Okay, so, yeah, I mean, but as we wait for this to run, yeah, you're getting me. I mean, I'm this whole question about, I have been meaning to do this thing with molecular computation. I mean, the question is, what do you do? How do you actually, so what are how do you, I suppose what you're doing is you're basically taking a bunch of chemicals, you have a large array of chemicals, and your operations consist of, you take bottle of chemical A and bottle of chemical Q or something, you mix them together. That's essentially applying A to Q or something, and that then gives you some other, presumably as a non-deterministic computation at some level, and presumably it has multiple products.
But wouldn't that always be commutative? I mean, if you...
Yeah, so what? I mean...
Well, then you probably cannot get a lot of stuff out of there.
No way, you can get plenty of stuff, because what will happen is there'll be some A's that apply themselves to Q's and some Q's that apply themselves to A's when you mix those two things together. And it may be that some part of what you get you don't care about, but that doesn't mean the yield, right? So the question is, what is the, when you're sort of combining these chemicals, the only issue is what's the yield, right? Because I mean, and also potentially, yeah, right. So I mean, the commutativity is not an issue, I think, because when you mix the two things together, there's just, I mean, there'll be many more than just two ways that they can apply themselves to each other, because there'll be many different chemical binding sites and so on. We've been curating this whole thing about name reactions for the whole molecular computation system, and I don't actually know the state of that right now. I don't think it's in 12.2, the whole collection of name reactions. But I think maybe we have the perfect storm of things that are actually do this, because between the Emerald Cloud Lab coming online, that actually allows people like me to do chemistry experiments purely from our computers, so to speak, and having them actually be implemented robotically, together with our chemical computation system. And I mean, because if I look at if I do a random, I should get a nice
SKK would be another molecule.
Let's try it. That would be really, you know what? That is the most absurd thing I could possibly imagine, is that we actually take combinator expressions and turn them into molecules. That is crazy. That's truly crazy. That is so crazy. Let's just pick an SK expression. Well, let's pick where is a good one? Hold on, I'll pick one up. That's not a good place for them. I need an actual combinator expression here, and I need to not be running it in this system here, because otherwise I will not be able to, because that's running that parallel computation. Okay, here, let me pull this into here. Fortunately, I have a new version here, so the different distinct binaries that are running. Okay, let's run this. Okay, so let's say enumerate combinators of 4, and let's say combinator traditional form of each of those. And unfortunately, this will probably have those combinator SK things. Let's see what happens if I say toString of each of those. Oh my gosh. Okay, so wow, that's a mess. Okay, so what I want to do is I want to say, boy, that has crazy, crazy stuff in it. How do I get the SK sequences without, but I don't even know whether molecule, I don't know whether, I mean, obviously this is not going to make a valid molecule, because this is just crazy. You don't get, 4 sulfurs don't go together like that. Oh boy, it's turned it into some hydrogen sulfur. Let's see whether it can do it. Let's see whether, I mean, this is just crazy. This is just a pun, basically. That is a ridiculous pun. Okay, so let's pick one of these things. Let's say SK of S of K.
We should use tungsten for some.
Tungsten
or Wolfram.
Not a highly reactive thing. let's just see what that one. S of K of S.
But then it would count as Wolfram research.
I know, and all those people who send me, we have tungsten for sale. You have no idea how many of those I get. Oh, well, okay, so it goes. I don't know whether you can have nested parentheses in the usual Smiles version of molecules. Probably wrong group here to answer that question.
I posted all the single letter elements in chat.
We do not need that, Ed. We really profoundly don't. This is just a pure piece of hackery here. Okay, so then this. Okay, so the question is, if we were to do this just with carbons, I mean, with S combinators, we could perfectly well make this. The issue is, I see. So an arbitrary S combinator expression. Let's just look at what this looks like. I am now very curious. If I take the combinator, what is the first non-terminating S combinator expression? Let's see, I can pull it up here. This is just in the category of, as we wait for the computer to compute, we're just hacking something absolutely crazy here. But why not? Okay, let me pull it in. Data, combinators, non-terminating. Okay, those are the non-terminating S combinator expressions. So if I say, but now I want to turn this into one of those parenthesized things. So if I say combinator, I don't know whether this is the best way to do it. Is Mano here by any chance? If so, she'd probably know how to do this.
She's not here, but I can call her in.
Well, don't bother, don't bother. I think this is combinator to list.
Probably combinator to application.
Yeah. I think that's a piece of code of mine. Oh, it's called function to application. Stupid. That's my mistake. Okay, so now all we have to do is we say toString of that, and then we do string replace. S goes to C, and the application symbol goes to nothing. Why is there big spaces there? That's really confusing. Well, in perfect hackery, we can just reduce the spaces out. Okay, so here, then, we would say, let me save this, this is too crazy. Okay, so now we would say to this, let's take this one here, I think, and let's say combinator evolve list, and let's say 5, let's take 10 of those. Okay, so now, and let's say to combinator string of expression is this guy here. Well, no, to combinator molecule you know, this is the problem with combinators. You just don't know where their parentheses end. Among problems with combinators. Okay, let's do that. And let's wrap a molecule around here. So now we say to combinator molecule. Ha, ha, ha. Okay. This is really, really crazy, but it's kind of fun. Wow. Wow. Now, what is that? Because the smile string, I mean, this is presumably a perfect representation in some, I don't exactly know what the smile string is doing. We have to ask one of our chemistry people. Let's take a look here. So if I say molecule plot, a molecule of CC, paren CC, CC, that should make, yes, that's right, that makes a chain. So CCCC, right. Why is there a side chain? I see, so there's one side chain. That's saying, but why is there 1, 2, 3, 4, and then there's a side chain of 2, right? So if I do that molecule plot here on %165, okay, so it's going to get a little crazy here as the Combinator. So if I do Combinator expression graph onto Combinator evolve list, wherever I have my Combinator evolve list, okay, so that's that. So this, in a sense, all that's happening here, I think, well, that's kind of weird, that that's so much simpler than this. Why is that? Don't tell me that there's a simpler representation of combinators graphically by using molecules. That would be crazy. What did this do? Why is that simpler? Because that is S of S. Oh, because that's these S's of S's are just the backbone here. I see. So it's a backbone and one side chain. That's right. But it's interesting that that's a simpler representation, isn't it? That's pulling these S's into the backbone, which I think you can do if there's only an S and no K. Is that right? Does anybody see that? Okay. It's okay, so Richard is commenting that SMILES is basically a depth-first traversal of the molecule graph after conversion to a spanning tree. But do you understand? Do you understand why this is simpler here? Because this looks like
there are no internal nodes. Huh?
Yeah, right. But apparently you don't need the internal nodes.
Well, is it unique?
Well, that's a good question. That's a good question. It may be unique. Right. Richard is commenting that you have to, where you break the cycles, but we don't have any cycles. These are tree graphs. These are tree molecules. I mean, dendrimer type things in the end, in this particular case.
It seems you can always push one of the descendants into the parent node.
I would think so.
Yeah.
I mean, I had thought about doing this. I for some reason, we got confused about doing it because I thought this would be a better way to represent these. You can always, well, okay, what do you do with this one here?
Yeah. Well, just one of them, but
that's not enough, isn't that's a different expression, isn't it? That's the expression S of S, right?
Yes. But...
So the expression here, so the claim would be for the molecules, if I were to say, oh, look, we're running finally. Molecule plot. Okay, let's say C of C. Ah, I see. Okay, look. This is not unambiguous. Right? Those are the same. Whereas for combinators, those are different. All right, so we don't quite get to do this, I think. But it's still kind of cool that we can make I don't think this can be, well, maybe this one is unique because it doesn't matter that we've got C of C. Maybe those are the same molecule for purposes of molecules, but they wouldn't be the same combinator. I mean, I think that's right. If you're thinking about these as molecules.
Yes, but this parenthesis is redundant C of C. You need at least two things inside the parenthesis. So here you would, yes, something like this. Okay, so that's not.
Yeah, but I bet that this case will do something non-trivial. No, it doesn't. Oh, I see. Oh, no. You need something else here. Then it will branch. Okay. Okay. The suspense. We're 1/3 of the way through the tens. All right. So let's get the tens. And did it actually gain something from its oh, come on, get down. Look at that time estimate.
Yeah, well, that's because initialization takes pretty much more time than running it.
Okay, so there
are a lot of very short computations.
Right.
And it looks like there's some issues with copying them to other kernels. Because I don't see, I mean, it shouldn't be slower than running it, definitely.
Richard is commenting that just like in the physics project, the canonicalization is variable. That's an interesting comment. That if you're dealing with molecules, yeah. I mean, obviously, for molecular, when we think about chemical reactions, we are basically thinking about multi-way systems as sort of all the possible reactions that can happen. And yeah, well, this deserves more thought. All right, let's just get this to run. I did not have my lunch, which is really so I think I've become very incoherent very soon here. That's my mistake for rushing to finish. I am trying to finish 4 documents, which have swelled to be, at least one of them is like 150 pages long, before the Combinator Centenary on Monday. In addition to the fact that we are hopefully getting version 12.2 out in the next very little while. So that yeah, I wonder what the best chemical, again, we have the wrong group of people here, I'm sorry, but the best actual molecules to consider doing these kinds of things with would be. Boy, this is a project, you know, I have this collection of projects that I've always wanted to do. And this molecular computation one is one of those. I mean, there's a list of about, you know, half a dozen projects that I've always wanted to do. That one I looked at pretty seriously back 20 years ago, and I almost started doing it. But then I decided that there wasn't enough ambient chemistry knowledge to do it. But anyway, okay, come on, run. Come on, don't hang up on some lost. That's crazy. Look at that, we're so close, 0.988. No, what is it doing?
You could probably go grab your lunch and it would be done right as you got back in 2 minutes.
Don't count on it. It's done. No, it's not done. Help. What happened? What's it doing?
It also needs to copy it back, I suppose.
Okay, there we go. All right, let's say length of FL 101 here. Okay, 400,000 items. Okay, all right, let's go figure out what the what this looks like. What did it compute, we ask ourselves. Okay, it's computed some very exotic beavery things there. So it computed 397,000 times. All right, let's see if it computed all of the enumerate lambdas 4,1. So let's see here. Well, actually, why don't we just do the following? Let's just say key select of %269 here of leaf count of hash equals 4. Well, we got them all, including the holdout, right? Which was that one, the 1 of 1 of 1.
Right, so those follow 6, 8, 10.
Wait a minute. Is that 1 of 1 of 1? No, that's
First
1 of 1
the
of
first
1.
one, yes.
And the step below happened in 8, and the step before happened in 6.
Wait a minute. So you're saying to get to 1 of 1, well, it's basically the nest of 1.
Oh, it's just we only have a few data points so far, but so far it's following that pattern.
No, but hold on a second. Hold on a second. What is this thing? This is hash 1. Am I right? It's that's the thing, isn't it? Nest that. Am I totally confused? Is this the right function? No, that's not the right function. It's 1 of hash, right?
Well, just 1. Nest 1, comma 1, comma.
Oh yeah, right. Okay, so it's nest. It's literally just that. What an obscure looking thing. Okay.
I mean, maybe we can find out what a sequence of combinators that kind of we can recognize how they generalize. I mean, there are 11 to choose from, and probably for each of these cases.
All right, let's just look at that for a second. Okay, but so in this case here, what we've got is, well, we for the next case up, just for fun, let's see how many of those we got, because we know how many there are altogether. Leaf count 5. Okay, we have got length of that is otherwise known as 6 of those, but the actual number, if we enumerate lambdas of 5, woof, is 14. Ed, mute your dog or mute your phone. Don't mute your dog, just mute your phone. Okay, so we only got 6 out of 14 of these. So the algorithmic complexity of these other ones is greater than 10, basically. So, but here you're saying, let's look at the, well, actually let's do our mem whatever plot. Let's do this plot here. How do we do this? We want, well, I see, that's of this thing here. We could compute just 1 of 1 for that case there. Okay, FL 101. My gosh. Okay, so now we say, there's a really stupid one there. Okay, so let's find min slash at min of first slash at %279 is again 6. So there's again a 6 case. Someone on the live, Yuri on the live stream is suggesting a canine version of the physics project. Wolfram. Never mind. The only question is, what is physics? What does a dog, which has much more olfactory knowledge of the world than we do, think? How does a dog think physics works? Okay, never mind. Let's look at this case here of. Okay, so in this, let's do this here, and let's say we want this, and then we want to say length of fixed point list, of Combinator fixed point list of that, and then we want to say, I always hate the fact that we can't get max of position here. How do we get the position of the maximum here? How can this be taking so long? Are we going crazy? Why is this taking so much?
How many are there?
Well, why is it taking so much longer than this one took?
Well, because you do the combinator fixed point list.
On a 500,000 items.
No, I'm not doing it on 500,000 items. I'm only doing on these cases here. You see? Look, up here, I did cases of FL 101.
Okay.
What did I do wrong here?
These are not that many, right?
Oh. Very big problem. Very big problem. I didn't apply it to an argument. That's the problem. So some of them didn't terminate, probably. Okay, so then let's say max %. Okay, position in 283. %, very inefficient, 1152. Okay, so let's get that, 1152. Not the most efficient way to do this, but there it is. There's our beaver. Okay, so let's say list step plot of leaf count /@ Combinator fixed point list of this thing of 1. Wow. That's a pretty, it's going to a lot of trouble to compute that result. As opposed to, let's take %283 position. Oh my gosh, that's a lot of ways to compute the same thing. So there's probably a bunch of K's in there, I would guess. By the way, another question is, what can we compute purely with S's? Can we compute any? No, that's of course the question is can we compute any function just with S's? Because we expect there are many functions we cannot compute just with S.
Yes, I mean you're missing all of the important stuff like composition, identity.
Oh, you think you are, but doesn't mean you can't construct that stuff.
No, I mean if you want lambda I calculus, you need other stuff.
So if I just say, if I use my lambda computing thing, so I don't think we can use Max's because his thing does S and K, right? So if I do...
Well, I mean, you can specify any rule there.
In your thing?
Yeah. Well, I mean, the function, the combinator final expression takes the rules as an input.
So how do we do... So I just want this done with pure S's.
Well, why won't it work already?
Well, because we're getting it to generate S and K expressions.
But that's a question for the enumeration code, which is not mine.
But the find lambdas, it says SK, what's that with leaf count? What are you doing there?
That's the same as enumerate combinators.
Okay, fine. All right. Why didn't you just call enumerate combinators?
Because I was very confused by it, so I renamed it. Because these are states of the combinators, not the actual combinators.
All right. Find S lambdas, let's call this. And then this leaf count would just be groupings of table of S, comma, leaf count construct arrow 2, right? All right, so if we say find S lambdas of 4, 1, that's not encouraging. All right, let's do a table of these n, let's do 7.
Well, the S can never go away, right?
Oh, that's a good point. So in other words, you're saying if we're going to do this, we've got to read out the answer in a more elaborate way. Right? In other words, we can't just read out the answer by having a pure, by just saying, do we have the answer here? We've got to say the answer is embedded in the object that is generated. Embedded in a kind of a coat of S's. All right, I think we should better wrap up here because I need to go back to trying to get things done. It's always good to have a centenary to force something to get finished, because after that I've got to get back to some. In addition to my, we've got some more physics stuff to do that I'm really keen to get moving on. And I'm now motivated, having done all this work with combinators. I think we can see some ways to do much better tracing of functional programming of execution, which I'm keen to pursue. All right. We got one more comment here on our live stream, I think, and then maybe we can wrap it up. Okay. All right, we should wrap it up here. Thank you all very much, and see you another time. Thanks, Max, Roman, etc.
Okay, goodbye.
Okay.